which is good. So it gives me enormous pleasure today to welcome everyone here to the IOA for this very special lecture on the occasion of Professor Hiranya Peiris taking up the chair, the 1909 chair of the Professor of Astrophysics. At these occasions, it usually falls on me to go through Hiranya's CV and to tell you what she's been doing, to give you a little flavour of her eminence. And of course, with someone like Hiranya, this could take a very long time. She is very eminent, but I will give it a go, because otherwise she'll be too modest to tell us all about all her successes. Otherwise. So she started her academic life here in Cambridge as an undergraduate in natural sciences, studying at Newhall, which is now Murray Edwards, which I'll come back to in a moment. She then did a PhD at Princeton before taking a prize fellowship at Chicago, and then came back to Cambridge for a couple of years on an STFC advanced fellowship. For moving down to London to UCL for a faculty position, where she was until coming here, but she also had a joint appointment as a professor in Stockholm, and she was director of the Oscar Klein Cosmoparticle Physics Institute as well while she was there. And she had many important positions along the way, such as vice president of the RAS. She's been a council member of STFC, many positions, had many prizes as well. Just in the last few years, she's had the Eddington Medal from the RAS, the Fred Hoyle Medal from the IOP, the Max Born Medal from the German Physical Society, and the Göran Gustafsson Prize from the Royal Academy of Swedish Sciences, something like that. Anyway, she's got lots of prizes. I could go on. I'm not going to go on and bore you. She got all this for her pioneering work in cosmology. She's the leading theoretical cosmologist of her generation. She has been doing groundbreaking work, pioneering methods for interpreting the observations in pioneering new data analysis techniques using Bayesian hierarchical methods and machine learning. I'm sure some of these she will be telling us about today, so we'll do much better than I can to explain them. But we're enormously proud of having welcoming Hiranya to the IOA to be our colleague, and we look forward to witnessing her successes that she will go on to, and I'm sure these will eclipse even the ones that I have mentioned today. I'm sure she will go on to every success, and we'll be very happy to be there for that. I did say I'd come back to Murray Edwards because she has come back to the IOA and to Cambridge, but she's also taken up a fellowship at Murray Edwards, which was her alma mater, of course. And Murray Edwards are co-sponsoring this event, which we're very grateful. And I say this is a very good, a great match between Hiranya and Murray Edwards, not just because of it being her alma mater, but also because of the shared vision that they have for encouraging and supporting young women into STEM subjects and to achieve their ambition to study. To study at university in STEM subjects. And of course, as the first woman to hold the 1909 professor, the 1909 chair, and indeed any endowed chair at the IOA, she is a true symbol of the progress that we have made towards equality, the progress towards equality, not quite at equality. There's a lot more that we need to do, but she's a true symbol of this and advocate for this. And something that's shared between Murray Edwards, Hiranya, and the IOA as well. Anyway, she'll be a true inspiration to everyone she meets, I'm sure, and a true inspiration to you, so please let me just hand over to her so that she can inspire you rather than having to listen to you. Okay. Thank you.
Thank you so much. Can you hear me in the back there? And those people standing, please do find a place to sit. Yeah, take your time, it's informal. And yes, I'm very happy to see this sea of young faces in the front. I'm very happy and honored to talk to you about decoding the cosmos today. And let me also briefly introduce myself. I'm a physical cosmologist. I have a very broad span of research interests, but they're somehow linked to testing fundamental physics with astronomical data sets. And in this talk, I will touch on some topics that I'm currently most excited about. To start with the most basic point, why does cosmology work? It's because light has a speed limit. So light has a speed limit, it's very fast, but it's finite. This means that when you look at even the nearest stars, light from those stars will have taken several years to get to us, so we see them as they were several years in the past. So looking into the distant universe is sort of time travel. And when you look out into the depths of space, we see the universe as it was in the past. So this allows us to see how the universe has evolved over time and to compare what we see with our cosmological theories. So you can roll back time in this way to the oldest light that you can see in the universe, which came into being roughly 13.8 billion years ago. And we call this the cosmic microwave background. So in an inaugural talk like this, the speaker is usually given some leeway to reminisce about the past. So I'm going to very briefly indulge in that to set the stage. So my start in the field of cosmology is tied to this ancient light. My career began with my PhD work. I was analyzing the first data from a NASA satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP. So this satellite delivered the first detailed sky map of this ancient light, the cosmic microwave background. And the study of this map cemented what we now call the standard model of cosmology. It's a model that's still described to this day, basically very well, all the data we have about the universe. A few years later, as you heard, I was briefly back here at the Institute as a fellow, and I was lucky enough to join in the analysis of the data from Planck, a European Space Agency satellite mission that was launched in 2009. Cambridge was leading the analysis of this beautiful data set. So Planck brought the early universe into sharp focus and refined our understanding of the cosmological parameters with pinpoint precision. An example is the age of the universe. So that's a question asked by humans since the beginning of history, and Planck measured it to 0.5% precision. So for the high school students in the audience, I want to give a flavor of how we use maps like this to learn about the universe. So in addition to amazing instruments like WMAP and Planck that can measure the sky, we also have theories that make predictions for what the sky should look like. We can't do experiments with the universe. However, we can calculate the predictions of what different physical theories with different physical ingredients would make the sky look like. And then we can compare those different fingerprint maps with the data and identify the one that looks like the data and rule out the theories that don't look like the data. So in this way, you can probably now appreciate a lot of heavy computation is involved. We need to calculate how this fingerprint looks like millions of times, and that usually requires quite a lot of supercomputing time. And we analyzed that data, and we found that there was something very surprising. All the information in all these pixels in the maps were described by just 6 numbers. So these 6 numbers tell us the shape, the age, the clumpiness of the universe, its constituent components, dark matter, dark energy, and just a little bit of atoms, the stuff that we are made of, and also when the first stars formed. When we got a lot of extra data from Planck, the parameter values were refined, but the basic model, these same 6 numbers, still described the data. So the model of the universe that describes the data seems surprisingly simple. However, this simple model contains 3 ingredients that are not in the standard model of particle physics. There's dark matter and dark energy, And the early universe was clumpy. So what made all of that structure in the beginning of time? Those three ingredients are not in our standard theories of fundamental physics. So the universe is simple, and yet it's really strange. The fingerprint in the cosmic microwave background is its so-called angular power spectrum, which measures how points on the sky are correlated at different angular sizes. So the reason that it's such an excellent fingerprint is that its physics is very clean. It's described by linear theory, and the impact of different parameters on the shape of the spectrum are very clean and relatively easy to disentangle. So I found this in my graduate school notebooks recently. This is probably the earliest plot that we made comparing the WMAP data with the model. So my job in the team was to develop the pipeline whereby the data was compared with the theory through the use of a statistical model. This was using a so-called Markov chain Monte Carlo approach, and we used that to infer the cosmological parameters. This approach is now really standard in the field, but in those early days it was very new, and we were sort of laying down the tracks as we went along. So the approach we were developing for WMAP is called Bayesian inference, and it really took off in astronomy once computational resources were sufficient to enable this idea of sampling on a very large scale. I would say that the WMAP analysis was one of the earliest analyses to trigger this phase transition in analysis techniques in the field. And Cambridge has a very rich history in the development of this Bayesian framework. Bayes' theorem is actually my favorite equation. It tells you how to update your prior knowledge in the light of new data. It's essentially encapsulating the scientific method in the language of mathematics. If our civilization was about to be destroyed and we could beam one piece of information to the stars, I would pick Bayes' theorem. Somebody was saying, ding, good. And this was Planck's refinement of the measurement of this fingerprint, the CMB temperature power spectrum. And it's compared to the best fit model in blue. And at the higher multiples, the error bars are so tiny, they're smaller than the points plotting the data. As someone who worked on pre-Planck CMB data, when I first saw the first version of the Planck spectrum, I could not wipe the smile off my face for like 2 weeks. The step change in data quality was so profound, and this enabled Planck to measure the cosmological parameters to percent or sub-percent accuracy. So that's setting the stage. So the starting point of the talk is that the study of the oldest light that we can see in the universe has revealed a simple but mysterious universe. So in the rest of my talk, I'm going to present some of the approaches that I will be taking in the next few years to help decode this cosmological puzzle. This is by no means a review talk or comprehensive in any way. It's just meant to give a flavor of the challenges that we face and the tools that we can leverage to crack this code. So while we measured the parameters very precisely now, the standard cosmological model remains phenomenological. So what is the physical nature of dark matter and dark energy? We don't know the answer to those questions yet. They together comprise 95% of the energy budget of the universe. So by looking up at the largest scales that we can see, we have uncovered deep holes in our understanding of fundamental physics at the smallest scales. So I'll return to the quest to understand these components a little later in my talk. We also don't know where did all the stuff in the universe come from. So the leading hypothesis is that a tiny instant after the Big Bang, a so-called scalar field, which we call the inflaton field, caused the universe to expand very rapidly by a factor of 10 to the power 26. We call that inflation. That's not what's happening to the economy today. That's what the early universe did at the beginning of time. So at the same time, tiny quantum ripples in the field got stretched out by the expansion of the universe to become the seeds of all the structure we see in the universe today. So inflation generates two types of fluctuations: density waves and gravitational waves. So over the past couple of decades, this inflationary paradigm has passed a lot of cosmological tests related to the density wave predictions. The smoking gun of primordial gravitational waves, that has still not been observed. It's a key target of upcoming CMB facilities, though, including the Simons Observatory, where Cambridge is a leading partner. So the next decade will be dominated by an explosion of data from electromagnetic sky surveys, and particularly by surveys of the cosmic large-scale structure. So this cartoon ties space and time with observational probes. So you can see late times going up to early times and small scales going up to large scales. And at early times and large scales, you can see the CMB, where, remember, most of our current cosmological understanding comes from. But later, and coming on in this decade, we are going to tile the bottom of this plot with probes of structure formation and evolution that are typically derived from large galaxy and quasar surveys. These probes overlap in time and scale, and they should help us piece together a self-consistent history of the universe. So an obvious way to view the universe is in visible light. There's a reason that our eyes have evolved to see the universe at optical wavelengths. That's because the sun has significant radiation output at those wavelengths. So starting in the 1990s, we've been mapping the universe in starlight in very deep and large-scale galaxy surveys. So this is part of the Sloan Digital Sky Survey. This is not a simulation. Each one of these galaxies is a real object. There are about 400,000 galaxies in this movie. And for me, the Sloan Digital Sky Survey represents the point in time when cosmology became a data-driven subject. The full size of this 20-year survey was not huge by modern standards. It's about 40 terabytes. An individual researcher can probably aspire to have 40 terabytes of storage these days, but it was still a watershed for the automatic acquisition of digitized survey data from the sky. So when we map galaxies using light, we see them arranged in this intricate cosmic web. This is because they're tracing huge filaments of dark matter that you can't actually see. You can't see 80% of the matter in this image. This is a slice through a simulation of how galaxies trace dark matter. So here is a simulation of the formation of a cluster of galaxies. So cosmological simulations are a key tool in understanding what our sky surveys are showing us. Using computer simulations, we can make detailed predictions for the fingerprints of different cosmological models and different astrophysical effects, which will alter how galaxies are scattered in this underlying scaffolding of dark matter. We can then compare those predictions with the data and figure out which of those theories match and which don't. And cosmological interpretation is increasingly reliant on evaluating these kinds of computationally costly simulations, which have many, many underlying parameters. And getting fundamental physics out of astronomical surveys is increasingly tied to our understanding of galaxy evolution. So I'll tell you a little bit about galaxy surveys now. Huge galaxy surveys will yield many of the cosmological probes in the coming decade. So these surveys can be divided into two types: spectroscopic surveys, where you get a high signal-to-noise spectrum for every galaxy, and therefore you get a precise redshift for every galaxy. But these don't go as faint or as deep as photometric surveys, which yield broadband colors from which a photometric redshift has to be estimated. And so these two types of surveys are complementary. I've had this slide for a while, and it occurred to me that we used to call these next generation surveys. These are the stage 4 surveys. It is a culmination of a program set in motion after the discovery of the accelerated expansion of the universe in 1998. But the future is now here. DESI has been taking data for over a year. Euclid just started its 6-year survey, and LSST will start next year. Roman is a little bit further down the line, but this is a very exciting time to be working in this field. And the project I'm personally investing most of my time on, and I'm very excited about, is the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which we call LSST for short. LSST is the ultimate big data project. As I said, it's starting operations in about a year. Rubin will return to every patch of the southern sky, roughly every 3 days or so, and do that for 10 whole years. And by stitching those images together, we will make a movie of the dynamic universe. This will enable us to study space and time in a way that's never been possible before at this scale. And it will expand the surveyed space-time volume by a factor of 1,000. As a comparison, I previously mentioned the Sloan Digital Sky Survey as a milestone in the field. And a single sky scan, this thing that takes 3 days from LSST, will be as deep as the entire SDSS over its 20-year lifespan. So that's the level of advance we are seeing here. LSST will enable diverse science missions at the same time. In addition to detailed studies of dark matter and dark energy, which I'm personally most excited about, it will do an inventory of the solar system. It will look for near-Earth asteroids that might threaten the Earth in the future. It will make this movie of the universe that I mentioned, and that will enable us to map the universe in cosmic explosions, the deaths of stars called supernovae, and identify the very rare and very precious counterparts of electromagnetic, counterparts of gravitational wave sources. And it will also make a very detailed map of the Milky Way, thereby in turn enabling additional studies of dark matter. So the resulting data set will contain about 60 petabytes of raw data, 500 petabytes of processed data. It's truly big data in terms of its volume, its rate of delivery, and its variety. So the Vera C. Rubin Observatory is named after a pioneering astronomer who established convincing evidence for dark matter from galaxy rotation curves. This is the first major astronomical facility named after a female scientist. It's about time, right? This amazing purpose-built facility is now taking shape on the summit of Cerro Pachon in Chile, where the skies are perfect for observing deep into space. This is where the camera will be mounted. It's the largest digital camera ever built. It's the size of a car. It will observe the sky in huge 3.2 gigapixel images. Each image will be like 3.5 square degrees. That's about 40 times the size of the full moon on the sky. And this huge structure is apparently so perfectly balanced that you can move it around with your hand without using force. I was incredibly lucky to be able to visit Rubin about a month ago. I joined this project in 2013. It was truly incredible to see how the engineering drawings that we were looking at for so many years have become a reality. And now we have to be ready for the data next year. So let's talk about that. What does it take to get cosmology out of data like this? In order to get accurate cosmology out of Rubin data or any photometric catalog, one needs to estimate redshifts for each source. This shows a reference spectrum and the filters of the Sloan Digital Sky Survey. So photometric catalogs that are based on imaging surveys, imaging means you just take pictures, you don't take spectra. Then you only get a few broadband fluxes through a handful of filters. And so that's a very lossy compression of the data, and we must estimate the redshift and its uncertainty from that lossy compression without having access to the emission lines. I know there are some people in the audience who may not have heard of redshift or spectra, but just think about it as trying to work out how far away each object in the catalog is so that we can use galaxies to map out the universe. So these are the forecasted target constraints from LSST on the question of whether dark energy is a cosmological constant or whether it's dynamical. Is it changing in time? So these constraints are obtained by combining several cosmological probes. And if we have controlled all of the systematic errors accurately, and it's a cosmological constant, you will see an ellipse in the center of the plot. And if it's away from the center of the plot, then that means dark energy is evolving with time. So even after 1 year of taking data, this ellipse is pretty small, but after 10 years, these forecasted errors are truly tiny. So then the question becomes, have we demonstrably controlled the systematic errors? And the accuracy of photometric redshift estimation is a central consideration here. And using this thorny problem of photometric redshift estimation as one example, I'm going to argue that machine learning is poised to revolutionize how we do survey cosmology. And here I'm talking about machine learning technologies that have literally become available only in the last few years. Those will make the difference. And I expect the pace of that revolution to accelerate. So machine learning has obviously been used in astronomy for decades. Example classic use cases are classification and anomaly detection. And the innovations that are rising in the field now have a different flavor. They're tied to generative modeling. So the examples I showed today include emulation. That's easy to understand. It's basically taking a slow computation and making it fast while remaining accurate. And there's simulation-based inference, which is leveraging the ability of machine learning to forward model the data very fast using neural tools. And then finally, explainable AI, which is a diverse set of tools for machine-assisted scientific discovery. This first example is really hot off the press. It concerns the redshift estimation problem that I highlighted earlier. And my collaborators and I have been trying to crack this problem for about a decade. And it was machine learning that finally allowed us to do so. This is work done with wonderful collaborators, and we pool diverse expertise, including cosmology, machine learning, data analysis, galaxy evolution, and statistics. So the question to ask here is, imagine you had a recipe for generating realistic examples of galaxy spectra and colors. What ingredients would that recipe contain? So the light that galaxies emit depend on its properties such as mass, its star formation history, dust, gas, metallicity, and so on. So there is such a recipe that allows you to predict both spectra and broadband colors of galaxies. It's known as stellar population synthesis. So what is stellar population synthesis? So in a nutshell, what you do is you compose the spectrum of the galaxy given its physical parameters. You add up the spectral energy distributions of all the stars in the galaxy at the right age and metallicity. And you compute the impact of dust emission and attenuation, nebula emission, and gas physics. It sounds simple, but it's worth noting that all of these ingredients that go into composing the SED are active subfields of astrophysics themselves. So in the work that I'm going to show you, we use the state-of-the-art ingredients that are present in the so-called FSPS population synthesis code, though it's possible that the results from this overall program will eventually help us improve the ingredients in the future as well. So why is this recipe important? Well, we realized that this redshift problem could not be solved unless we solved another, more general and harder problem, which is to be able to faithfully model the diversity of galaxies in the survey. I'm convinced that in order to get fundamental physics out of galaxy surveys, ultimately you need to understand the galaxy population. Our ambition was to learn the joint distribution of galaxy properties in the universe with the redshifts. So this problem is not actually tractable with traditional sampling-based methods like the ones I briefly touched on earlier. You have to consider that even the current catalogs of galaxies we have hundreds of millions of galaxies, let alone LSST's billion galaxy catalog. However, modern machine learning methods can straightforwardly and accurately describe the complicated web of interdependencies that occur between these galaxy properties. And you can do that quite faithfully. And these tools have become available literally in the last few years, essentially over the pandemic, a silent revolution happened. The first part of solving this problem was quite straightforward to crack. The SPS model calculations are relatively fast. They take 1 to 2 seconds on a CPU. So you might ask, what's the big deal? But the use cases require billions of evaluations. So the first thing we had to do was to speed up the computation of the spectra and photometry using neural emulators on GPUs. The way that we did that is not leveraging these new ideas. It's a standard neural network. The architecture we developed yields sub% accuracy and speed up of factors of 10 to the 4 in a state-of-the-art 16-dimensional SPS model. The architecture is pretty versatile, and it has been later adopted for other use cases like accelerating the computation of cosmological power spectra. So a key point here is that this neural model, because it's captured by a neural network, is differentiable. So that means you can take gradients. And this point will become crucial in an upcoming step. And this is the real innovation. It's the use of flexible neural models to capture the complex web of dependencies between galaxy properties. So here we use a score-based diffusion model. This is a powerful type of generative model, but it's very simple to describe it to a physicist. It is basically first trained to learn how to degrade a complex high-dimensional distribution to a simple IID Gaussian distribution through a diffusion process. The diffusion process is essentially Brownian motion. So what you're learning is a stochastic differential equation. And then once you have that, you can do the inverse process, which is reverse Brownian motion. That's an ordinary differential equation. So now we have a method whereby we can draw samples from a Gaussian IID distribution and generate samples from the complicated high-dimensional distribution. So that is really crucial. So now we have all the pieces to train our population model for galaxies. We can draw a sample of galaxy properties from this diffusion prior. Then we use the emulator to draw realizations of galaxy observations. Then we can add noise. The noise can be as complicated as you want. And then now we have mock data. And to compare with actual data, we have to apply selection. The selection can also be as complicated as you need. You can, if you don't have simple selection, you can learn it in terms of a machine learning classifier as well. So now I'm going to play the simulation here. This is just a 2D toy example. But basically, because we can take gradients through the emulator, we can minimize the distance between the 2-point clouds, one being the data and one being the mock data, by comparing a distance between them called the optimal transport distance. And so basically, as you minimize that, the population prior, the diffusion model, is basically becoming a generative model of galaxy properties in the real universe. This feels like an approach that will generalize to many other settings, where state-of-the-art parametric inference is becoming increasingly challenged by similar issues of computational expense and high dimensionality, model complexity, and scalability. So we have now calibrated this model with the Cosmos 2020 catalog, which is the best available catalog for the purpose. This has about 140,000 galaxies, characterized in a very broad, 26 broad and narrow bands, going all the way from the near UV to the mid-infrared. And it's complete to quite a deep magnitude of R less than 25. And that's a very good match to LSST photometry. It's already deep enough to do LSST with. It should provide a faithful model of galaxy properties to redshift of about 4. We expect it to extrapolate beyond that as well, but we have not tested that, so I'm not going to claim that. So now we have an end-to-end framework for simulation-based inference with galaxy surveys. So in this plot is our predicted redshift distribution for cosmos. Of course, we don't have deep spectral data with a simple selection in order to validate that. So I'm showing you a comparison with a state-of-the-art SED fitting code called LeFair, which has hand-tuned population priors. So what we're comparing here is essentially the hand-tuned population priors with the population prior that we have learned through that previous framework. Despite the very uneven nature of the LeFair histogram, I can talk about the details of that if anybody cares later, the match is pretty good. So to our knowledge, this is the first time that the full joint distribution of galaxy properties has been estimated from a large, complete galaxy catalog. And with this model in hand, we can predict the properties of any catalog with any filters of comparable or shallower depth. And as a bonus, we obtain full information on the evolution of galaxy population over cosmic time in terms of a 16-dimensional state-of-the-art SPS model. So we are now deploying this approach in a new weak lensing analysis of the KIDS catalog to provide a benchmark against traditional approaches. And we hope to be ready for Rubin first light in January 2025. I'm going to bet on us. Now I want to briefly touch on the potential of explainable artificial intelligence in cosmology. This very brief example, but I'd particularly like to highlight the work of Lucy Smith, who's doing very exciting studies in this space. So the goal here is this grand thing called machine-assisted scientific discovery. But I'm going to just show like one example of what we brought to this. The key idea is to present a machine learning architecture, which we called a supervised variational encoder with raw three-dimensional simulation data, and to guide its training so that it learns to answer interesting questions about structure formation. And the key feature of this architecture is the part in the middle, which is called an information bottleneck. It's essentially a low-dimensional latent space. And after doing this model compression, which is like a nonlinear version of a PCA, we can try to interpret what this model has learned as encapsulated within this latent space. The first problem we applied this to was to understand the building blocks of dark matter halo profiles. So the density profile of a halo describes the distribution of the dark matter within the halo, and these halos form within cosmological simulations. First, you have to basically define what is a halo boundary. That is typically an empirical definition. And then you plot the density in spherically averaged shells. That's what you see on the plot. And this is a key ingredient in cosmological analyses, for example, in cluster cosmology and lensing and beyond, for example, in dark matter direct detection. So we trained this interpretable variational encoder to predict the density profile of dark matter halos, given the 3D density surrounding the halo, using a representative training set of halos. So the network comprises of this encoder, which compresses the 3D input density into the lower dimensional latent representation, capturing the information required to answer the question, which is to predict the dark matter halo density profile. So the network readily discovers the dimensionality of the problem. That's already impressive to me. 3 latent variables are necessary and sufficient to describe the full diversity of halo profiles. 2 are related to the standard NFW parameters, in case you know what that is, and 1 is new, describing the outskirts of halos beyond the R200 radius. So what has the machine learned within these latents? So in order to understand this, we computed the halo assembly history of all of the halos in the dataset. It's really important now to remember that during training, it never saw that information. It only saw the final state of the halos at redshift of 0. And we wondered whether, in spite of that, the degrees of freedom that have been learned by the network related to the halos mass assembly histories that had been encoded within the density profiles. And the answer was yes. The analysis showed that the building blocks discovered by the latents have clear relationships with different and specific aspects of the halos mass assembly histories. Interpretation of these outskirts latent is a new machine learning enabled discovery. It's actually truly remarkable that it's only 1 degree of freedom that captures the outskirts of halos. So since the 1990s, we have known that dark matter halos exhibit self-similar universal profile shapes. But the physical origin of that near universality is not well understood, even now. And it actually took me by surprise how well machine learning methods helped us to add new insight here. So these findings will now, we will use them and we'll take measurements from future surveys of actual density profiles, and we'll be able to back out the information about those halos assembly histories and also conduct new tests of the nature of dark matter. So to finish that part of the talk, a key goal in cosmology in the coming years is to be able to reliably access the rich information in the cosmic web and use it to stress test our understanding of cosmological physics, which, remember, derives largely from the linear physics describing the cosmic microwave background. I hope I've given you a glimpse into how modern machine learning methods can do some heavy lifting here, and they've arrived just in time to do that. These methods allow us to actually embrace the complexity of the problem rather than fighting it. And I also believe they can assist us in gaining new insight, as with the previous example. Now I want to talk about trying to understand dark matter in the sky and in the lab. So a key unanswered question in cosmology is, what is the dark matter particle? There are many creative theoretical approaches to this question, but there are 2 broad candidate theories: weakly interacting massive particles, or WIMPs, or axions. These are particularly attractive because they also solve major problems in particle physics in addition to providing a dark matter candidate. They haven't been invented for the purpose of being a dark matter candidate. So much of the experimental effort in past decades, I think mainly for sociological reasons, has focused on the WIMP hypothesis, and that parameter space is basically closed off now. And it's only more recently that experimental attention is turning to the axion. So there's a huge part of the axion parameter space that's relatively unexplored. Cosmological data can bring something to the table here. It can constrain light dark matter, including ultralight generalizations of the axion, as well as sub-GeV dark matter. And a little bit later on, I'll return to hunting the axion itself in the lab. So I'm now going to very briefly touch on cosmological tests of ultralight dark matter. And the reason I want to bring that in is it was enabled by this idea of emulation, accurate and fast surrogate models. It was truly a pleasure to reconnect with not just one, but 2 former students in carrying out this study. So the Lyman-Alpha forest is one of the large-scale structure probes that I mentioned earlier. It's an ideal probe of dark matter signals which manifest at smaller scales. But these signals can also be potentially mimicked by intergalactic medium astrophysics. So trying to separate out this gastrophysics from the fundamental dark matter signal is a little bit of a mud wrestling exercise. So modeling the data sufficiently accurately to be able to do that separation requires intensive hydrodynamical simulations. In this particular study, it was basically 3,000 CPU hours per simulation in a 12-dimensional parameter space. So our key innovation here was to build an accurate surrogate model by using an approach called Bayesian optimization to decide where in parameter space do you run those expensive simulations. I think we had time to run about 50, and we needed to place those very carefully so that interpolating between the points where we have simulations, it enabled us to constrain the ultralight axion mass using the Lyman alpha forest. And this analysis improved the state of the art by an order of magnitude. And we were able to robustly disfavor the canonical mass range of this model. That model outside the canonical range, which is favored by naturalness considerations, is actually quite vast. And other people are still exploring that. But for me, the model is dead. I move on. We also set strong model-independent limits on light-dark matter in a mass range where direct detection experiments have limited sensitivity to sub-GeV dark matter. The main point of these figures I want to kind of highlight is that you can see on these plots cosmological, astrophysical, laboratory, and direct detection limits on the same plot. This highlights the complementarity of cosmological and particle physics constraints in this challenging task of trying to understand the physics of dark matter. So, it's an inherently interdisciplinary field. So now I come to my favorite dark matter candidate, the QCD axion. So the QCD axion is a compelling dark matter candidate because it was not invented as a dark matter candidate, but to rather solve mysteries related to the standard model of particle physics, specifically the so-called strong CP problem. So the standard model has the neutron electric dipole moment as a free parameter. When you measure that, it's tiny. So it appears very fine-tuned. Physicists don't like fine-tuning. So the axion was proposed as a dynamical way to explain this fine-tuning. It's meant to wash away the problems of the standard model. It's actually named after a detergent. So this type of dark matter has wave-like properties that relates to its mass. How can we detect this? So the axion has a very, very weak coupling to photons, particles of light. We could wait for several times the age of the universe for one axion to decay into 2 photons. But if you're very impatient like me, we need to actually try something else. We could pump many photons into a very strong magnetic field to induce this decay. We need many, many axions in a given volume so that there's a reasonable likelihood of conversion. So finding the axion is a little bit like tuning a radio. The Compton wavelength of the axion needs to match the wavelength of the photon to get the conversion. And this induces a tiny, tiny, tiny electric current. So even with a 10 Tesla magnet, which is very, very strong, it's still a tiny electric field that is induced. When the mode of the cavity matches the axion wavelength, we see a peak in the electric power. So that's how you look for it. But this is the latest state-of-the-art plot showing constraints on the axion-photon coupling versus the axion mass. And if you want to be solving the strong CP problem and the dark matter problem at the same time, you want to be on this yellow line that's highlighting the QCD axion. You can see most of this parameter space over many orders of magnitude in mass is unconstrained. That's because it's very difficult to build and tune the cavities that you need. For a given cavity experiment, it's a particular size, right? So you can drill down to explore a very narrow mass range, but it's very hard to scan across the masses because you're constrained by the resonant frequency set by the geometry of the cavity. So higher and higher frequencies probe larger and larger masses, but this is inversely linked to the volume. So at some point, the volume is too small to contain enough axions to enable this conversion to generate a signal, and you can't probe any higher masses. So ideally, what you want to do is you want to break the relationship between wavelength and frequency to allow you to build high-frequency systems with an effective wavelength, which is the same size as the cavity volume. So the key idea is basically to give the photon an effective mass using an effective medium, which is called a metamaterial. A metamaterial is just a designer material that allows you to control the dielectric response. For example, you replace a shape of a cavity by a whole bunch of wires. That's a metamaterial. So you want to control the dielectric response, so you can change the effective mass of the photon to obtain the resonance, rather than changing the geometry of the cavity for zero photon mass. So this was the brilliant idea that was actually conceived by two postdocs at a journal club at the Oscar Klein Center, where I was previously director. They then fleshed it out with Frank Wilczek, who's actually the inventor of the axion, in a very exciting paper in 2019 that immediately attracted huge attention. So my involvement in this project is quite different from the other projects I'm showcasing here. My role was to, well, one of the things was to come up with the acronym for the project, ALPHA, which I'm very proud of. Frank came up with CRAB. I think alpha is better. So you take your wins where you can get them. And the other thing was to attract R&D funding and to help set up and support an international collaboration that would bring this idea to reality. And unlike many other examples in physics and astrophysics, the R&D showed that the idea was even more promising and viable than the forecasts in the original paper. So we are currently experimenting with different wire metamaterial resonator prototypes. This is PhD student Heather Jackson with the Berkeley prototype. This is the Stockholm PI, Johan Gudmundsson, in the lab working with postdoc Gagandeep Singh on a different prototype design. Note that these are truly tabletop experiments. The magnet facility is also the size of a university lab. This is in contrast to truly gargantuan particle physics experiments that one commonly comes across. I previously mentioned tuning as an issue for the traditional cavities, but using a wire metamaterial actually enables tuning as well. Because, for example, you can change the plasmonic resonance by changing the spacing between the wires so you can scan across frequencies. Here's another idea we are trying out through rotation of shaped wires, which we call sails. So where do we actually look now? So there are two very well motivated regions we should target. One is the gut scale QCD axion, and that's still a bit hard because actually there is no unique prediction for its mass, so you would have to scan a huge range. And the second is the post-inflation axion. For the post-inflation axion, there's actually a very specific prediction for its mass. It's only limited by our ability to calculate it. So it's a very difficult calculation involving simulations of the decay of global cosmic strings in the early universe. The latest calculations put it at about 65 micro EV. That's about 15 gigahertz. This is out of the reach of conventional cavities, which top out at about 5 gigahertz. But it's accessible to our plasma telescope. And I'm delighted to say that as of this year, ALPHA is a construction project. It's targeting the post-inflation axion. This has been funded through the generous support of two US philanthropic foundations, the Simons Foundation and the John Templeton Foundation. And ALPHA will be hosted at an existing high-field magnet lab at Yale University. Cambridge is a founding partner because I moved here. And we have the responsibility to carry out R&D on superconducting wires, which initiates a new connection between the Institute of Astronomy here and the Cavendish Laboratory. And this comes at a very exciting time in the dark matter landscape in the UK. The UK is actually positioning to bring a big dark matter experiment to the Bulby mine in the Northeast. I personally truly believe that ALPHA is capable of making a groundbreaking discovery, and I'm excited to grow Cambridge's role in it in the coming years. In the final few minutes, I want to go back to the beginning of the universe and confront you with a truly startling prediction of inflation. So theories of particle physics with a unique vacuum are hard to come by. Spontaneous symmetry breaking gives rise to multiple vacua. And there's also strong observational evidence for accelerated expansion, both in the late time universe, where we call it dark energy, and in the early universe, where we call it inflation. So these two facts strongly motivate that we inhabit an eternally inflating multiverse. In this picture, most of space, on scales much, much larger than the observable universe, is trapped at a high vacuum energy, and it's still inflating. And inflation only ends locally by tunneling to a lower vacuum energy. And this phase transition happens via the nucleation of a bubble. So this could have been the birth event of the universe. These ideas can sound uncomfortably like science fiction. Many cosmologists actually regard them as science fiction and prefer to keep their heads down and think about more mundane matters. And for some cosmologists, the prediction of a multiverse is a red line they won't cross. They'd rather throw out inflation altogether. So I've spent quite some effort in my career to look this uncomfortable prediction in the face and try to find ways to test it, because that's what science is. We had to be able to test things. So it may sound surprising, but there are potential tests, if we are lucky, through signatures between the collisions of these bubbles. A totally new window opened up just last year when pulsar timing arrays announced evidence for a stochastic gravitational wave background. Bubble collisions are a possible source for such a background, and this is also a target for the amazing LISA space mission that the European Space Agency has just adopted. But the main hurdle standing in the way of even testing these ideas in principle is that our understanding of the relevant theory is just not good enough. These are like really difficult calculations. It's as if the universe took all the hardest maths you can think of to describe nature and bundled them all into one problem and told physicists, okay, you go and do something with that, you know? So there are many assumptions and approximations involved, and we don't know which of these are justified and which are not. So a new approach that we are taking to understand the theory better is to emulate the same physical equations, but translated within an analog condensed matter experiment in the laboratory. This involves ultra-cold atom systems that are called Bose-Einstein condensates, where phase transition in the laboratory system can be measured and compared with predictions from the cosmological analog theory. So by comparing our maths with the experiment, we can refine our theoretical understanding. So this was a really clever idea, first proposed by experimentalists working in New Zealand a few years ago. And my collaborator, Matt Johnson, and I learned about it at the Aspen Center for Physics, which is a fertile ground for learning about new innovations in other fields of physics. And we set about putting together a collaboration with the diverse expertise needed to understand the details of the right experimental conditions that were needed to realize a faithful analog of early universe relativistic first-order phase transitions in the laboratory. We were lucky enough to be doing this work in an era when UKRI is enabling cross-disciplinary collaborations. And we obtained the funding to engineer the system in the lab, which behaves like a quantum field undergoing vacuum decay. And a prototype experiment is currently taking shape right here in Cambridge in Zoran Hadzibabic's cold atom lab in the Cavendish. It's a very messy looking universe. And I don't know if you can see where it says science cell there. So the BEC has condensed, and it will shortly be transported along that glass tube into the science cell where we can start taking data. So if I was giving this talk a few months from now, I could have shown you actual bubbles nucleating in the lab, but what I can show you are computer simulations of what the bubbles would look like in the experiment versus our best understanding of the very early universe. And by tuning the experiment in different ways, and by turning the analogous knobs in our mathematical calculation, we can see whether our expectations are correct. For example, for how the rate of bubble formation depends on different physical properties, or what is the likelihood of a bubble nucleating right next to another one that has nucleated. Obviously, that's a very important consideration if you want to work out what is the probability of bubble collisions, for example. So this is a fairly unique collaboration that exists at the intersection of condensed matter physics, experiment, and cosmology theory. So even just thinking deeply about this problem before we have any data to compare with has led to advances in the understanding of the theory beyond the standard approaches. So I have to say, I have to confess, when I was an undergraduate at the Cavendish, I was so bored in the condensed matter course that I used to fall asleep in the lecture theater. But something must have gone in. I'm very grateful to this university for my broad education in physics and for instilling in me the curiosity to pursue research questions wherever they lead and not to be confined by narrowly defined disciplinary boundaries. So I want to finish up by emphasizing that our understanding of the universe requires interlinked progress along 4 frontiers. So recent progress in the field has been driven unarguably by technological innovation. This is producing enormous volumes of data, very varied data that we need to model accurately and contextualize in terms of fundamental theory. I hope I managed to convey an impression of how this interplay between theory, observation, and experiment plays out, and hopefully convince some of the younger members of the audience to join us in this quest to decode the cosmos. Thank you.
Thank you, Hiranya, for a fascinating talk. You've covered so many different areas there. That was amazing. Not quite got to exoplanets, but
no, one day I'll get there.
Everything big, but it's going down small on tabletop as well. Very fascinating. Have we got any questions? We'll get the microphones.
So I'm a huge advocate for the advances in machine learning. I guess this is kind of a philosophical question of what will it take for, let's say, we demonstrate WA is non-zero, but only through machine learning approach. What do you think it would take to convince people of that as being true?
That's a really good question. I think one of the things that is true, not just for machine learning methods, but any methods we're deploying in cosmology in this very complicated setting of galaxy surveys, is that they're very hard to validate. And one of the things I don't have a full answer to this, but one of the things we've been bringing to the table is we are developing basically a set of techniques in parallel to our machine learning methods, where we are doing model checking directly in data space. So for example, you can think about this as a generalization of cross-validation, where you predict new data sets that you haven't used in the training, and then you directly compare that in data space. These days, this happens in the space of cosmological parameters, and I think that's way too late, and that is going to subject us to experimental bias. So in the case of this pop cosmos model, for example, we've developed new methods that are based on QQ and PP plots, quantile and probability plots that work in arbitrary numbers of dimensions, and you directly compare your predictions to the data. So that's one answer I can give you, but I think it's a general question to which there is no general answer. It depends on the problem.
Yeah, sorry.
So a slightly off-field question, but to help us get a feel for these Bayesian hierarchical models that you mentioned, what sort of fields outside cosmology are they used?
I think they're used for any field where population modeling is a factor. What it actually makes a very special difference in physics and astronomy, though, is that we have compelling physical models to do the forward modeling part. Whereas in many other fields in which you're trying to do population modeling, there isn't a first principles forward model that you can have. So they're particularly useful in cases where you have some kind of physical or domain-based understanding or a model that may be able to predict the data. Does that make sense?
It does, thank you.
Thanks. Yes, a student.
Yeah.
Thank you. for the very interesting talk. I was very fascinated by the last part, where you mentioned about the possibility of the universe emerging as a sort of false vacuum decay. And the first time I encountered this idea in my studies was when looking at something which has perhaps gone a bit out of fashion today, which was the search for the wave function of the universe in the 70s. And in particular, the tunneling condition proposed the universe starting as a bubble creation event. So I was wondering if you think these experiments and the resulting conclusions on the cosmological side of things could give us some new insight into that problem and perhaps allow us, if not to uniquely determine, at least lead us on the right path towards finding out what's the quantum state and wave function of the universe.
I hope that one day it could, but currently what we're trying to do is to understand even the calculations that come from the idea of doing false vacuum decay. For example, if you use instanton methods that entail symmetry assumptions, so a bubble pops into being. It's not a real-time process, it's just Euclidean time, so it suddenly appears perfectly symmetric. There's no way of calculating what is the likelihood of a bubble right next to you, which is something we really wanted to find out. And those kinds of calculations, we just don't have the mathematical tools for. What we have developed here is a real-time approach using a semi-classical idea. So where you put all of the quantum physics in the initial conditions and you evolve through the classical equations of motion. And that's how we're trying to make progress. And that's called the truncated Wigner approach. That may not encapsulate all aspects of quantum physics, but it's certainly much more than what you can do just with more analytic-based tools. And we want to be able to understand, can we describe this experiment, which we can tune, and it is a nonlinear quantum dynamical system that we can engineer to do vacuum decay in different potentials, for example. And so I think what we're trying to do here is to calibrate this semi-classical approach so that we can make trustable predictions for it. And then we can come to questions of, can we even test it in principle? Yeah. Any questions from the front?
There's one at the
Okay, yeah.
One at the very back. I mean,
Yes.
a bit of a naive question, but
No worries.
showing the axion coupling and
Yes.
mass body. If you go back to
Yeah, I can go back to it.
where you,
This one?
Yeah,
Okay.
when you were showing a parameter space, so I presume that yellow line is sort of what's been conceived by particle physicists where it needs to be on, right?
Yeah, that's right.
So how far down beyond the plot does it extend? Like beyond the
It probably, like, you know, the axion photon coupling at the bottom of that plot, I mean, we will never be able to access that probably, but crucially, the post-inflation axion is not down there, it's up there, okay? So basically this other plot I showed was just at the top part of that, you can see that this is at a higher mass, and it is at a stronger axion photon coupling. And that error bar on the calculation, you know, you probably have to take it with a tiny grain of salt, but it's probably around there. And we can for sure get to that one. And so this, I think, is a very nice sort of marriage between theoretical predictions which are sharp and well-defined and experiments which can go out and test it. So that's why I like the post-inflation axion. And it's one of the two most compelling parameter spaces there is. Indeed.
The other one might still hide behind experimental.
The other one, basically, the problem is that there isn't a clear prediction for its mass, so it can still scan over a large range of masses. Indeed. Yeah, what we have promised is we're going to test this one.
Was there more questions? Does Matt?
Yeah, so you talked about using naturalness to guide your search to this dark matter parameter space. Like, I know some particle physicists are now maybe arguing that naturalness is not necessarily a good guide to reality. I don't know what your thoughts are on that.
I think when it comes to dark matter, for me, it still is. To take it back to the kind of more multiverse type ideas, maybe not. So it depends on what is the question. And in my case, I don't like models that had been invented to sort of try to explain a new observational fact. I like generalizable theories. And so both WIMPs and axions fulfill that. But then there are generalizations of the axions motivated again by theory. And it's, you know, I won't go back to that plot now, but basically there's a very, very broad parameter space for the ultralight axion. But it's only one part of that that's theoretically motivated. So that's the one I was motivated to test. But I'm very happy if other people explore much more widely. Hi.
So, if our path finds the axiom,
Yeah.
so if you're discovering particle physics, cosmology, change physics, and all that, what can we see if it does not find the axiom?
You know, looking and not finding is not the same as not looking. And I think that we learned something by ruling out the post-inflation axion. That leaves one other well-motivated parameter space, which is the gut scale axion, in my view. And then we will have to do that entire scan over many masses. So for that, okay, if you give me like a 50 million price tag, then I can probably do that. We have 5 million here.
Fair enough. I wish I could.
Thank you.
CERN, after a lot of taxpayers' money to build a new ring, sorry to ask a controversial question,
That's okay.
but do you think this will likely tell us anything useful about the questions that you're raising?
You're talking about what comes after the Large Hadron Collider?
Exactly.
Okay, so I'm not a particle physicist and I don't want to rain on their parade. I think the field has not solidified on whether they want to go to greater luminosity, which is more discovery space, or precision test, which is a different kind of collider. And those are two different options that they have now, and they have to decide between them. Without any guide from theory, I would personally go not for the discovery space, which is not perhaps that huge without guiding from theory, but rather to explore the details of the Higgs and its coupling to other particles, which is a different type of collider. But I'm not in charge of making that decision.
Yeah, okay, well, let's draw this to this question set to a close. There's time for more questions outside with wine and nibbles. So please do join us, and please do join me as well in thanking Hiranya again for a very fantastic